Okay, so welcome everybody. I hope that you had a bit of time to complete the different training exercises. And I think what we could do is to go one by one, one group by group, and try to explain where you are at the moment, what were the main achievements, what were the difficulties, what still are the remaining difficulties, and so that other people can profit from your, first experience manipulating this type of system. Okay, so maybe while the other are presenting, please switch off your microphones, and we may interrupt. So if you want to speak, switch on again your microphone, and we may interrupt. I think it would be more lively discussion if we can just discuss between each other. It will make more sense probably. Okay, now we need some sort of order. One of you wants to, is burning to present some stuff. Nobody? Fab? No, Fab? Mona is going, let me see. Mona, you are trying to connect as well? Okay. Okay, Cara. Okay, Fab, would you like to start? No, we don't hear you, Fab. Fab, we don't hear you.
We can start here if needed.
Okay, Fabrice, for some reason we don't hear you. Maybe you can see what happens.
The microphone, maybe.
Okay. Cara, you would like to start?
If needed, yes, we can start.
Okay, so Cara, please go ahead. Fabrice will reconnect. So this was a joint project, so between Cara and Arthur, or different. You made two different projects.
Yes, we tried to work on everyone on his side, so it was like that. But the both projects will join by the end.
Okay, be careful with the Larsen effect together, because you have two microphones opened.
Yeah, yes, I think it's okay now. It's okay now.
Okay, good. So Cara, please.
Okay, well, so the aim of my project was or is still to apply the gravity effect on the whole tree. So I explain how it should be done and how I did it, and where I have some difficulties. So to start, I first built the recursive tree, as you might see here on my screen. Then with this class which calculates the mass, the inertia, the rigidity, I could at each step I could create a stem, then give a length to this stem, and by the end I have I have a derivation length which is high. It's about it's 200 length to 200 time a loop like that, and then in each step I calculate the mass, or I mean the torque on the in the stem by doing backwardly. I mean here, for example, for this stem, I go from here, from the apex at this level, and backwardly calculate the torque, and then I calculate forwardly the displacement, the mechanical displacement for each stem, and by the end I can get the gravity effect. I will make a little animation so that we can see what it does right now. Just okay. Well, we can see here the effect. So for time being, the limitation of my models are, first of all, I don't apply correctly the direction, direction of the displacement. For this, I mean, if you see me, if I'm like that, the gravity effect should be applied like this.
In the vertical direction.
Yes, in the vertical direction. As my stem, I had coded the direction. The limitation of my model is that I hard coded the direction, which means if I'm in the side, the effect will try to do like that. Rather
Okay.
in the side. So this is the difficulty on which I'm currently facing on my model, and also I have a little error, which is like that. The whole tree it's not built in the axiom. I mean before the production. For that, I'm accumulating a little error, which is not in fact too much, but anyway, if I want to be more accurate, this means I should build completely my model tree in the axiom before going to production. So I don't know if it's a little bit clear, and if you have any question, we can.
I mean, please, everybody, if you have questions or remarks, do not hesitate. I have. Yeah. So, do you think that you are about to have because it would be super nice to see the whole tree bending upon gravity? Do you think you can manage to reach this stage?
Yes. I mean, if I can get correctly the direction of each stem, and apply this and apply this placement according to this direction, it will be okay for the whole tree.
Okay.
This is the missing part.
The direction of the stem is provided by the head of the turtle. So
by the head.
Okay, so the head is a vector.
Okay.
In 3 dimensions that provides you the direction of the current segment where the turtle is at the moment. So it's very simple. I mean, go back to the sessions and see how you get the head.
Okay.
Yes, but
okay.
It only gives one vector, and around this heading vector.
Yes. So if you want to have the whole stuff, you have the frame command. that would return, or HLU, that would return the three different vectors.
Yes, because it's a z the z vector in the world that we have to rotate to get the direction of gravity in the branch frame.
In case you don't get where I am concerned is here.
Okay.
If you see in my screen, so this plus alpha, this plus should depend on the orientation. As you know, plus mean I turn to I turn to left, yes, but where I am exactly, it may be the correct direction which I should retry and apply here. So actually, I tried different things, but it's hard coded. It will be good to make this.
I see. Your problem is that actually the plus and the minus, they are relative angles with respect to the current frame of the turtle.
Yes.
Okay. Which means that the turtle can be in any direction. If you do a plus, you will rotate in this direction. Or
yes,
in
yes.
this direction. Okay,
yes.
but not relative to the vertical direction. Whereas
Exactly.
what you want to do is to rotate relative to the vertical direction. So
exactly.
I think this is what Arthur was suggesting. You need to rotate, but not in the local frame of the turtle. You need to rotate in the global frame of the laboratory frame.
Okay.
So we can see this. Okay, I see. It's good that you have identified exactly where is the problem. And obviously, this might be a question of some minutes to solve. It shouldn't be difficult.
Okay, well.
Okay. Thank you very much, Cara. Arthur, would you like to continue?
Thank you.
Yes, yes.
And Cara, the problem that you have comes from the fact that in the original model, the banding was applied in 2 dimensions. So the plus was used and did the trick because the plus was exactly the direction where we should apply the banding.
Yes.
But no, as you are in 3 dimensions,
yes,
plus doesn't work, and you need to generalize what was done before.
Exactly. Yes.
Okay.
You can disconnect. Okay, so I was kind of in the same project as Cara, but with a different method. Whereas Cara would use a mechanical computation inside the prediction rules. I had decided to do the whole mechanical computation outside of the prediction rule, and then inform the interpretation rules with the results.
Okay.
So what I did is, first of all, I replaced. So this work is based on the recursive tree example from the course. I replaced information from the internode with which were length and radius with a class that I called mechanical data. But it also has the length and radius, but it also it has in addition the Young modulus, the density, and then the deformation for the visual part. So first of all, I had to extract the tree from the L string. So I did my own little turtle to walk the tree and extract the different branches or internodes. So yeah, well, I won't go into detail, but I'm just looking for beam pattern is internode. I'm looking for internodes and rotations. And as I move along, I update the rotation matrix of the branch inside the world frame. And I create children's, which are what I call the tree mechanical structure. So the tree mechanical structure is it's a recursive, it's like a recursive structure where each object is actually an internode, which has a point A and a point B.
So these would be the endpoints of each segment.
Yeah. Point A is at the bottom, at the bottom, and point B is at the top, and each branch or internode has a parent or node, which is the root, and children's. And so we can just work recursively the tree for static resolution and deformation.
Mm.
So getting the position is quite simple. It's just A plus, so the turtle is always pointing in the X direction. So it is point B is point A plus the length times the X axis in the branch frame.
Okay.
Uh,
So actually what you have made is a sort of additional turtle.
Yeah.
Okay.
So I'm getting point A and B coordinates in the world frame.
Okay.
Yeah, I decided it would be easier to get everything in the world frame at first.
Uh-huh.
To have because we need to know well, the direction of gravity and everything, and
Okay.
also it was easier to debug because we can see here it's here, it's in the world frame.
Okay.
So once we have the tree, we can do the static resolution. So static resolution is computing the forces which apply on the internode on points B and A, as well as the torques. So it's not, well, I won't go too much into detail, but it's from the top to the bottom.
Okay.
To the root, because the mass of each internode applies on the next.
Okay.
And then we can do the local deformation. So for deformation computation, I used beam theory. So, because I figured branches were good enough beams. But for that, I did have to get into the local frame. So that's why we have some rotations here. Then just computing the displacement. Well, I did that by hand, but so it is. So I get the displacement in X, X, Y, and Z. But I only took into account flexion and compression. So for now, there is no torsion, but it would have been interesting. And then I compute for now just an equivalent rotation. It would be the deformation angle, which is what the interpretation rules uses.
Okay, how do you communicate between the LPI system and the?
And so it's here. At the end of each derivation, yeah, I pass the S string to create the chemical structure.
Okay.
So maybe this should not have been here, but when it's parsed, there is the static resolution once, and then the local deformation once,
Okay.
which is another weakness of the project now. And then I modify the S string, meaning I modify the parameters of the internodes by just going through it. So S string self-point index, so it's to select the correct internode. 0 is for M data, mechanical data, and deformation equal the result of the deformation. So it's just changing the S string in place, because actually I didn't really know if I should return something or not at end each, because it's not really it's not well defined here.
No, well, it's just a card for summary.
It seemed to work to modify in place.
Okay, and
so
how do you use the? Okay, so you get the piece of information that corresponding to the deformation for each segment.
So the deformation is used here. So I get the information. I want that as Euler angles to have a successive rotation around X, Y, and Z. And then I just append the rotations before before putting the the branch.
Okay, very well. So is it working at the moment?
Yes. This is a result.
And would you have the?
So the small branches here is just to represent the previous the polarization of the branch without deformation. It's just here. It was to visualize.
I didn't get what. Sorry, I didn't get this.
So
yes, the small. Okay, I see.
This is the not deformed branch.
Yeah.
To better visualize how much it bent. And so see what it gives. So we can see it actually bends in the right direction, mostly.
Okay, bending in this case is only in the vertical plane. Is that correct?
No, actually, maybe.
You wouldn't have torsion.
Yeah, I didn't have torsion yet. That's true. But there is flexion in the other plane too.
Okay.
So maybe there is a bit of flexion. It is not pure vertical. So, however, there are some limitation to my work for now. So, as I said, there is no torsion, even though it would have been interesting because there is quite some lever here and there. I only do one pass, but if I was in the small deformation, it would be correct or correct enough. But as you can see, it's not really in small deformation.
Okay.
And I already quite boosted the mechanical properties of the tree.
Yeah, yeah. Can we try something?
Yeah.
Can you go in the scalar, which is on the left-hand side? Yes, you have the scalar stuff here. Yes. Can you write? Can you? I think this is right-click. Yes, a new integers. Yeah, integer. Then you put elasticity, something like this. Value will be between yes 0 and 100. Let's say it's okay. Okay, and now you multiply your Young modulus by this value, elasticity.
Like that.
Okay, now you go in the L system menu on the left hand side of yes here, and you click auto run.
Auto run.
Yes.
Okay.
Yes, and now you click on the elasticity. Yes, exactly here. Double click or no, yes, to edit, and then you move this. Ah, okay. Could you? Yeah. Can you?
So maybe I will. I already reduced quite a bit the density to. So how do you?
Okay, so if you yes, continue. If you increase or decrease,
it makes me drop the bar each time I.
Yeah. So the idea is that by controlling this slider, you would increase or decrease the elasticity of your tree, and the auto run will launch the simulation for each change in the value that you make by sliding your bar. And this would maybe you see that this has an effect on the result of your tree.
Yeah.
Okay, so it's a way to see the amount of deformation if you change one parameter. Okay, so this is a tree not deformed.
A bit, but not much as well.
Not much, and then you can increase this value and deform the tree.
I would never want to go to that much. I mean, the value is 1. There you go.
Okay, so we can see this together because I think it may be that this was very the way you communicated between the two, between the L system and the static tree outside was very well done. Maybe we can improve a bit the way it was done when we get together, but I think the overall result is super nice.
Yeah, I had other ideas because if I'm using Bem's theory, I can actually I have the curves of deformation that we could extract and put to configure
here.
Here, yeah.
Okay, very well. Thank you very much, Arthur. Shall we skip to I don't know, Fabrice? Are you still?
I can try. I don't know.
Yes.
Yeah.
No, you. We can hear you.
Okay, so we had. Okay. So on my side, so I think we have to make something joint, maybe Christoph, because what I will show you is definitely not really fancy and not really LP models. So what I did was to continue my work on calibration. So with the idea of making the Arabidopsis model more realistic and scaled to a real Arabidopsis. So what we did, so I worked jointly with Christoph, and so we went through the model. And so basically what we realized that so in Christoph model, so each organ is encoded. And basically what you have is a starting, so the first idea was to get typical lengths, okay? To scale it to the real plant. And so what we did was to go through all organ definitions, like in the flowers, like sepal, petal, stamen, gynoecium, the leaves, the internode. And so from my data, both using either the real pictures and my measurements. So we try to get the real measures. And so you remember, so you have this hill function. So you start from a point up to, so the organ will grow from a starting length up to a final length. So the initial length is a bit arbitrary, okay, because everything happens here in the meristem, so you don't see it. So the real important thing was to get the final length. So that's what we did. So it's a bit a long work because you've got many different organs, and for each organ, so you've got the length, the width, the diameter. So you've got several things to evaluate. Okay, so this was the first work that we did, and once we did this, so we first generated like let's say a first trial of a scaled Arabidopsis, and we are not completely satisfied because even if you scale like the flower, okay, if you've got flowers here, um, but the final growing virtual Arabidopsis does not necessarily look like the real one. And what we realize that the coordination of the different parts is really key here. So to make a very resembling plant, what is really important is how let's say the developmental dynamics of the flower is synchronized with the internode. So for example, I will just give you two examples here. So you see that here in the inflorescence bud, so you've got little flower buds, and then the flower opens, okay, with now you see the petal, for example, but you see that when you see the petal opening, the flower is outside the inflorescence bud. And so, for example, the first time we made the flower grow, like this flower was not like here, but it was like still inside the inflorescence bud. So it means that we need to synchronize the growth of the petal here, so that it only goes above the sepal growth when it's outside the bud here. And to be outside the bud, it means that internode length should be of a given length, okay, a minimal length. So it means here, like just to achieve this behavior, like the flowering flowers are outside the bud, it means that you have to synchronize the growth of the different flower elements, sepal, petal, stamens, and gynoecia, with the internal length. Okay. So that's the first thing. And the second thing that we did is that, for example, you see that also on this very on the same example here at the tip, to make a tip resembling to a real Arabidopsis, we realize that the pedicel, which is here the little stalk that links the bud to the stem, has a very strange dynamic. So it is first straight, and then when the flower is maturating and it's opening, it's acquiring a bell shape here, and then soon after the pedicel is going the other way around and is soaring up again. Okay, so this dynamic of it is upward, bending down like a bell, and going up again. So we have to first to mimic this pedicel dynamic. But if we mimic this pedicel dynamic again with no link and with no synchronization with internode, then the bell shape here will happen either too early in the inflorescence band or too late. So we have to synchronize it. Okay. And we have to do this for, so here I focused on the tip of the plant. So I focused on the tip of the plant because, for example, we had feedbacks from David and Ayan telling us that they had some issues with a machine learning algorithm to recognize the tip of the plant. So we are quite interesting to model here the tip of the plant. But we are trying to do this work for the branches. So here that's the same. So we are trying to model the branches here and to model the delay between the dynamics of the main stem here and the branches. So right now, that's what I'm doing here. For example, in my in the table you see here, I'm taking all the pictures again. And here what I'm trying to count is, for example, here in the main stem, you've got before the transition to flower, you've got different branches. And in the second order, here you see a branch, and before the transition to flower, you've got also different branches. So here I'm, initially I did not count this, but realized that for the model and the synchronization of the delay between the main stem and the lateral stem, we need to have an idea of, in a branch, how much lateral events are produced before the transition to flowering here. So that's why here I'm taking back the pictures I took, and I'm counting when I can, because it's not always obvious, but I'm trying to count the number of events of branching lateral. Here it would be a third order branching before the transition to flowering. Okay. So this is just to give you the idea of the work we did, and maybe I can stop the sharing. And I don't know, Christophe, if you have just maybe.
Yes. So if you stop sharing, so we have not finished the work because it's quite
it's longer than we.
It's quite long, and we have to discuss several times with Fabrice in order to make it consistent and complete.
I'm lost with Zoom. I cannot go back.
I think there is usually an independent small bar on which you need to click to stop the sharing.
Ah, yes, because I switched. So okay, now it's good. Sorry.
It's okay?
Yeah, it's okay.
Okay, let me see on my side. Oh. It did. Sharing. So. Do you see anything?
It's uploading, I guess. Yes, it's coming now.
Can you see anything?
Yes, now it's good.
It's good. Yeah. Okay. So what we did with Fabrice is that we took the measurements, and for each organ, you see that I can show you the type of data that we have. So, for instance, for the we created a separate file for each organ, and the idea would be to describe the dynamics of growth of this organ for each one of the organs in which we are interested. And then, because they are composed organs like, for instance, flower is made of sepal, petals, and carpel, and etc. So we made the same thing, but in a way that is consistent with the fact that the organ is made of smaller organs. So for a simple organ, it comes quite easily, let's say. I have, okay, I need to zoom in. So here, all the measurements have been made by Fabrice. One grid square is 1 centimeter. So here you see that the sepal is like 2 millimeters high, which corresponds to actually here you see that the length is, so the initial length is 0.2 centimeters, and the final length is 2 millimeters. So if you run this, what you have is a petal that is growing from the initial length to the final length. And in between, there are stages that are controlled. And then between these stages, there is a linear interpolation. Okay? So we did this for petal, for sepal, for petal. So for petal would be this. So it's more whitish, but I can put the... Okay, so this would be the petal again. Okay, and now all the ratio between the length, the width, etc., they are all controlled to be in agreement with the measurements in the field. Okay, so there is similar thing for the carpel, and then we have the flower, which is a bit more complex because the flower starts to synchronize what is in the sepal, what is in the petal, the orientation of the organs in the space, and how they are synchronized during their development. So, for instance, if I just select, so Fabrice was showing, let me, where is it? Yes, so if I synchronize all the organs together, it will go like this. So you see this is the very young flower bud. Let me put this like this. So we have already all the organs present, but they are very small, like in the very young flower. Maybe after that, Fabrice, if you can show the drawings that people have made of a very young flower with the young organs. Yeah. But before that, I will just finish this. So you see here, or maybe I should. Okay, so here, I managed to, what I did is I made the different stages of development. They are all synchronized. And you see that there is a time here, which is, sorry, 0.3. So meaning that this 0.3 is a timestamp. It's not the real time. It's a timestamp for this stage of development of the flower. So if I want to refer in a subsequent higher model to this moment of the development, I will call the flower model with this timestamp. So if I want to have for instance, the moment where the carpel is going to, where the petal are going to get out of the sepals. So I need to look at the timestamp, and the timestamp would be this moment, which is 0.2, you see? Okay, so in this way, I have a simple timeline that makes it possible to make a reference on all the developmental stages of my complex organ. Okay. So now what I can do is that I can call this in a more complex system. So the more complex system is the flower plus the pedicel. And you will see, so you remember that Fabrice was showing that the pedicel can bend and then can start upright, then bend, and then get back to the vertical position to some extent. And then, so this is a model that we could call the full flower, where you see now that there is this small pedicel at the basis. And now the full flower will go this way, where it's the flower plus the pedicel, and both have been synchronized. And together, they define a developmental stage to which we can attach a number, which is indicated by the number at the bottom. So for instance, if I grow this, okay, you see that the sepals are going out. The system is start to bend. Maybe I should open this a bit more. Now you see that the carpel is getting out of the system. And then the whole leaf, the whole flower will grow back again. And then you see that thanks to this, I have been able to synchronize, for instance, the fact that the petal and the sepals are falling away before the system gets back to the upright position. Okay. And okay. So if I execute this in a more, let's say, rapid manner, it's like this. Okay. And here again, it's virtual time. It's not the real time. It's the time, let's say, a time that makes it possible to order the different events to all together. Okay. So there is no meaning in the actual time animation that you see. Okay, and now I didn't get yet to the whole integration of the system, but I have yet another stage. Where is it? I think this is this one, where you can see the whole thing. It's not yet well synchronized. It's not realistic yet, but it was the first try yesterday. Okay, so this would be it's not yet calibrated so that it fits with real data. It's the first integrated system, but I can replay this for you. So you see that all the elements are now synchronized to the growth of the internode. So it's not the realistic values that we have here, it's the first guess, let's say, but you see how the system is growing, which is funny because we think of the growth of plant as something that is more or less static, but actually you see that it's very dynamic in a way. Okay, and now, so the last would be the whole integrated system, but it's really on the way. So I will show it to you just for fun, but it's not yet finished at all. Where is it? So this needs to be really improved, and we have maybe one week of work with Fabrice to really polish all this, but it gives you the first impression about all that. So here the flowers are getting out, the petals are getting out of the sepals too rapidly. It's not yet, as Fabrice was pointing out, and you will see that the different element will bend. as the internodes are elongating in the young flower buds. Okay, so this is very preliminary. It doesn't yet integrate every aspect of the system, but it sort of gives you the overall direction in which we are going. Okay, Fabrice, I give you back the.
Yeah.
Sure. Here. Do you want to add some words, Fabrice?
Yeah, that will be very short, but so maybe to give an idea of yeah, the limits and the work plan. So as I told you, so our first objective was to scale the plan, so to extract typical lengths for everything. Then we realized that, okay, it's not only typical lengths, but typical time and typical synchronization. So we are all trying to synchronize the different elements of the plant. And so this led us, and especially Christophe, to make an extension of the hierarchical time warping that he presented you during the course, and to like to be more systematic in the way that the hierarchy between the different the synchronization of the different element is encoded in the LP model. So now that's what we are trying. So, and once we will have the different for each part of the plant, so we will have all these timelines and the hierarchical links between the different timelines. So we hope that we'll make a realistic growing with typical lengths and typical synchronization time, let's say. And the final idea would be to maybe to incorporate variation in this, because what we have is typical time. So it's mean values. So from my data here, I estimate like a typical petal length, typical sepal length, a typical delay between the flowering time of the main stem and the branches, for example. But of course, in my data, I have statistics and like the real distribution of values. And so we will try to estimate, like in the second time, the variation of this model to make like a realistic variation. Yes, so that's a bit the working plan. And just to say that when we were trying to do this work, we realized that so in most of my data, you see, I'm mostly focusing on the architecture of the inflorescence, but we realized that we had to go like even in very fine details, like even the kinetics of development of a flower, which was a bit overlooked in my first experiment, because okay, I'm not interested in what happened in the flower. But hopefully, like this work has been nicely done, because like developmentalists in the 90s, so they worked a lot on the development of the flowers to study the cellular events that were taking place in the meristems. And so we have a lot of data, like so, and so we went back to typical seminal papers, like in the 90s here, where you had these growth curves of the sepal petal stamen. Okay, and for example, so it's now a typical textbook, the Arabidopsis book, the Arabidopsis book, sorry. And for example, so you have these different stages. And in these different stages, so it's really well described. So, and you have like, so the development of each organ of the flower is described. The relationships, so from this you can infer, so it's not described per se, but in the paper you can infer like the synchronization between a sepal development here in green and the gynoecia in the center in yellow, for example. So we went back to this, and from so here you can try what Christophe explained you, like you can try to run the first the flower separately. So in a way, what Christophe showed you here was this. It was a rerun, a replay of this development timeline. And now what we are trying to do is to add the pedicel, for example, and this dynamic of the very funny a bending and upward bending and upward again, bending of the pedicel. And then when we have this, we are trying to incorporate it to the growth of the entire stem with the leaving of the flower from the inflorescence bud, for example. Okay. And so yes, there is like so what we are trying to do in a way is to extend this work that has been nicely done like almost 30 years ago in the flower, but for the entire plant, and to stage every step of the development of the IIL part of the plant, and to synchronize the different parts together. And so here you can see that you have like a really nice job that has been done with typical pictures, when you can see the different developmental stages of the flower, and you see in the flower like the development stages of the sepal, of the petal, etc., etc. And so we use this a bit with Christophe. So we are not as detailed, because for us, for example, what really matters is when the flower starts, when the sepal starts, here when the petal goes beyond the sepal. So for example, in a way, in Christophe model, we are jumping from stage 1. So we are simplifying this, and we say that what matters is stage 2, let's say, when the flower is first visible, then stage 4, when the sepal are visible, then stage 13, when the petal goes beyond the sepal, and then stage 15, when the carpel goes beyond all other organs, then stage 17, where the flower is withering, and the petal and sepal are falling down, for example, etc., etc. So we are trying to catch up like typical stages that are like meaningful in our scale, which is a bigger scale, and that help us to capture most of the dynamic of the plant. I think that's all.
Thank you very much, Fabrice. Any questions from others? No? Not yet tired? David?
Sorry.
Yes.
The bending dynamics is really funny, but it seems in the model it's not yet, because there is a upward pointing fruit which still has a S shape, right? In Fabrice image.
Yeah, it's true. So here again, I think that maybe so it's true that the model is still not realistic, so we have to work on several aspects of the model. So here Christophe mainly worked on the dynamic of the pedicel, and the final shape of the fruit is not well reproduced. So that's why maybe in the end you've got a kind of S shape that is not modeled. And anyway, it might be also linked to the variability that I was talking about. So something I would like to capture is the variability of the fruit, for example, in length and in shape. The bending of the entire, so if you take a higher scale, the bending of the branches or of the main stem also. So in Christophe model is mainly, so the main stem it's quite straight, and the lateral branches are like only bending up, and in reality it's much more wavy in a way. So we have to model this, and so it's a question of how we model it. Do we is it only through variability and standard deviation, let's say, of a typical mean shape, or do we incorporate more complicated shapes for different organs? So it's still an open question.
No, but still, it's great if we get better tips for machine learning. It will be great. Yes. And I think something you didn't touch is the leaves, because leaves are also an interesting topic. But I understand that it's already a lot of work to do the inflorescence. Yeah.
But you're right, it's on the agenda too. So we would like, especially maybe the colline leaves. So I think, so right now we might leave the realism of the rosette a bit, apart, and try to focus. So I have several images, and so if we can first, it would be the same, like to to get typical lengths and get the dynamics, synchronize the dynamics. So that would be great. But then in the leaf, so you've got not only the typical length and final length and synchronization with the entire plant, but also the final shape, which is quite complicated because it's rolling, and it's rolling in several dimensions. So you've got in the transverse axis, it's rolling on the edges, and also like in the longitudinal axis, so it's rolling at the tip of the flower. So you have a double rolling and twisting sometimes. And so I don't know if we can model this correctly, but we'll see.
One point that we will be able to study together, when I say together is with you, David, and with the group in study, is up to what extent we should be precise in the modeling of the flower development or of the plant development in order for the machine learning algorithms to be efficient.
Yeah.
At the moment, it's absolutely not clear. It's unclear what should be the limit. But we could make based on what we are doing at the moment, making, let's say, plants with very accurate precision. We could try to degrade these plants at some point and check whether this degrades or not the machine learning training.
Yeah.
So this maybe we can do this in the forthcoming months. Let's say once we have finished this model, we can start this.
Yeah. Okay.
Okay. How about continuing with Jeanne?
Sorry, I will have to leave in few minutes.
Okay, so maybe we continue with you, David.
Yes, please. But I must say I was in vacation for quite some time. Plus, I went to visit some place in Portugal, etc. So, to be honest, I didn't improve much the model. But I will show you the model we developed with Christophe during the workshop. So, as you may remember, I went to the market to get some carrot leaves, and I wanted to reproduce the carrot. So you see here the animation of the carrot. So we've got the leaves, and we've got the root of the carrot itself. And so to go through the model, we first set the tropism to some value, and it's pointing upward. The elasticity, sorry, we set it to some value. Then for the number of leaves we choose, which is random, we generate a leaf, and we choose the angle of the leaf randomly, and then we produce the root. Then, depending on the derivation step, we change the orientation of the tropism so that we get this kind of wavy shape for the bending of the leaves. And so, at first, the direction of tropism is upward. Then there is this, which is quite convenient and which I had a hard time to find, and it's Christophe who hinted me that it could be done this way. When the derivation step is between 1 and 4, I take a random tropism direction, which is the current orientation of a stem plus some Gaussian noise. And so this is the way to do it, like to access the heading direction of the turtle. I use this, and then when derivation steps are so at the tip of the leaves, I take a tropism downward to have the leaves fall at the tip of the leaf. And then so if the order is 0, so at first order, you have branching which is opposite, I think, like 2 branches at the same point of the stem are branching. So and if the order is higher than 0, then you've got, I think it's alternate branching, where you've got one leaf, an internode, and one leaf again. So you see the difference between here and here is just that you have an internode between the 2 leaves here. Then there is a growth of the internode, and to interpret the internode, we use a length and a radius, which is given by measurements of at least for the length. I did measurements of the internode depending on the order, and so depending on the order on the derivation step, we take the length to be a sigmoid function of the derivation step. And so I fitted the parameters based on the measurements, roughly based on the measurement. And then there is the root. So here you've got the production rule for the root, and the interpretation of the internode for the root. So we change the radius of the cylinder and the length of the cylinder, so that it looks like a bit like a carrot, like you see here. And so what you see is that I don't have time really in the model. So everything depends on the derivation length, on the derivation step n, and so that makes the growth not so realistic compared to biological growth. And also you see that the carrot root is not growing like a carrot root. Like it should be thin and long at the beginning of the development and grow in radius at the end of development. So this could be improved. And yes, and then what I would like to do next is maybe produce other vegetables to make a farm. So as I already mentioned at the workshop, I would be interested in lettuce, but maybe we should combine LPI with Blender if we want to make lettuce. But I'm also, if you have ideas of vegetables which could be fit for LPI, I'm happy to try it out.
You didn't have a field of carrots?
Oh yes, I had a field, yeah. But I didn't added randomness to the field.
Okay, we can
you see,
we can do without the randomness. We can imagine the randomness.
Well, wait, I'm not sharing. Yes, so here is the field of carrots, but they are all the same for now. But yeah, it's easy to change the randomness.
Okay, would be nice to have this randomness, because no, it seems that everything. Yes, okay. Okay.
Yes, and so I don't know how you want us to contribute to the deliverable, but maybe I could write a 2-page explanation of the carrot model with a few images, so that
This would be super. Yes, yeah. And then maybe I don't want to push, but and finish the randomness stuff.
Yes, yes.
So that you can have the field in the end.
Yes, yes.
Would be great. Yes, would be great in this way. Okay, thank you very much, David.
Okay, sorry, I have to leave, but thanks again, Christophe, for organizing this this week and this session.
You're welcome.
And,
you know what?
Sorry?
You know what? Augustine already almost finished to the videos. So they should be available quite soon, actually, on some.
Ah, really? Oh,
Yeah.
cool. But, so it will be uploaded on YouTube?
We didn't actually know at the moment. He uploaded them on YouTube somewhere, which is private. So I can look at them, but in the end, probably they will be uploaded on YouTube. But we need to decide this together with Jonathan and Peter.
Okay.
Everybody.
Okay. I think Peter will be interested to have a look too. Yeah.
Okay.
Yep. Okay, see you all. Goodbye.
Bye. Okay, so shall we proceed with Jeanne now? And then we could go with André Claude, and then we finish with Mona. Would this be okay, Mona?
Yes.
Okay.
So what do you see now
Your screen.
with LPy?
Yeah.
Okay, that's the one. So so last time we saw with one another, I started the MOS life cycle model with only the protonema. So to remind you a bit, the MOS life cycle starts from a spore that you can see here. And then we're going to see filamentous structure expand with a color map that shows the cellular differentiation that happens in those filaments. And then we're going to see the transition towards the gametophytic phase of the MOS with the leafy shoots emerging. So let's see how it goes. Okay. So there is a lot of randomness everywhere in my model. Oh no, it's gonna run first. Oh, that's gonna be, oh. Sorry.
You can disable this.
Yeah, yeah, because I cannot do. Like you can pause when you are doing the animation, but you cannot stop when you're running. So every time I need to restart LPy. And I have this kind of issue.
Yeah.
I'm just gonna make a little trick like this. Because now he's initiated, and if I run, I animate, it's not gonna run in the entire thing.
But you can there is in the preference you can disable this behavior.
Yeah, I will do this, but okay, so we have protonema filaments that start germinating. Actually, we have underground filaments and surfacic filaments. I should precise that it's not roots, it's really a vegetative structure. But I had to make different modules so that the underground ones that explore the milieu do not make leafy shoots. Then we see a bud emerging and the leafy shoot starts growing. You can see the metameres, which are, phytomers for plants, which are composed of an internode and a leaf and a bud that you cannot see. And the metamer length increases with time. And so what is random in this model is there is a probability to branch depending on your age, your order of branching, and your cellular differentiation stage. You have a probability to make a bud, a gametophytic bud, depending on your cell differentiation stage. well, yeah, that's
And
it.
what defines the cell differentiation stage?
In the Protonema filaments, you have first chloronemal cells that are represented in dark green.
Okay.
They are full of chloroplasts. They are made for photosynthesis. And then with time, it differentiates to colonemal cells, which are represented in lighter green, which are longer cells which explore the milieu. So there are many things, really many things to improve in this model. For example, there is I guess there would be less chloronemal cells in the ground because there is no light, for example. Also, I'm not sure my probabilities work well because I always have gametophytic buds emerging a bit too soon.
And there are some segments also that are changing completely the position, which is a bit weird sometimes.
Yes, that's the apical cells. There are little details like this which are not realistic, and I need to work on them.
Yeah, yeah.
But there is self-avoidance in the Protonema development, which is what I had shown last time. But I also have issues with the self-avoidance system because, well, if I put a radius, if I try to put, so to explain how the self-avoidance work, as the apical cell evolves in the domain, it's gonna leave points that are memorized by the system. And when an apical cell is growing, it has a cone in front of it. And if it detects a point in this cone, it's gonna stop growing. But the points are established at a regular interval, and you can go in between. So you can cross a filament if your points are not close enough to each other. But I had an issue that I didn't understand, which is that when I try to increase this number of points to get more continuous representation for T-cell avoidance, actually my apical cells stop growing even if there is nothing in front of them. So I think there is something I do wrong.
Okay.
The mechanism behind the growth of the leafy shoots is actually auxin based. I took a model that I already had with a diffusion of auxin from the sources that are the apical cells, and a branch emerge when there is a minimum of auxin. So I can show you if I switch the axiom to directly a gametophytic apex. So you're not going to see any protonema. And instead of showing the plant and the leaves, I'm going to show the auxin concentration. Then you're going to see how it works. So here you have the apex that's growing. You have the color map that shows the concentration of auxin. So at the yellow apex, there is the maximum concentration of auxin. Then you see here you had the minimum, which made the branch emerge. And then you see the branching pattern emerge. So yeah, so this is the, let's say, the skeleton of the leafy shoots you saw earlier when I decided to show the auxin and not the plant.
Super, super.
And I didn't yet model the last part of the, I mean, we cannot say there is a beginning and an end because it's the principle of a life cycle, but in this model, the end would be the sporophyte. which emerges from an apical cell once the plant has been fertilized. So at the end, you would see the sporophyte, which is most often a brown stem with a capsule at the end, which contains all the spores, which then would again be spread, and we would start again from the sporious, so at the beginning.
Very beautiful. Thank you very much, Jeanne. Any questions to Jeanne?
Yeah, Jeanne, in your branching here, it's the phyllotaxy is random, or do you incorporate?
The phyllotaxis is not random. There is growth by plastoquron, and I have a phyllotaxic angle alpha, and that each plastoquron, a phytomer is produced with a bud at angle alpha. Yeah, no, that's it.
Okay, and so here, if I understand well, at each phytomer, so you've got a bud, but the bud is not growing. It's not always growing. It's growing only when you've got a minimum of auxin. That's right.
Yeah, actually, the bud is an artifact I needed for LPI, because in mosses, it was never shown that there was actually dormant meristems. But because the phyllotaxy is not random, there must be a mechanism that's where it grows. So in LPI, I had to force it, but yeah. So I make the transition with if there is no, are there any more questions?
Don't think so.
So I will make the transition with the André Claude model, because we worked a little bit together. And as he had the idea to make a metabolic model for the emergence of inflorescence architectures, I participated by showing by giving the diffusion process. So where you have basically it's a finite difference modeling of diffusion, and you need to specify the context where you have a branching, so it diffuses in all directions. So I worked with André Claude to use this diffusion in a different model and adding sugar. So I will let André Claude take over.
Thank you very much, Jeanne.
And I need to come back to.
Okay, so yeah, so initially my idea was to look at ways to recapitulate different patterns of inflorescence with fewer parameters, if possible. In the end, is it not working? It's, oh, I need to allow the, so it kind of works, but basically you keep adding more parameters, which is not very satisfying. I need to, sorry, it doesn't want to share my screen. Maybe I have to do this. And okay, I have to, whatever. Does it work now? Yes, it should work. Sorry. Okay, maybe do you see my screen now?
Yep.
Okay, sorry. So this, in the end, what indeed, after discussing with Jeanne, we decided I could take what she built, and she actually implemented the extra sugar production and diffusion. So this is the same plot. It's kind of not so pleasant, but what you see here is the concentration of sugar actually instead of auxin. And if you, what is interesting is that you can, for instance, change the pattern just, for instance, by changing where a sugar is produced, which kind of makes sense. So here it is produced only at the apices, with the rule that says the bigger the apices, so the order defines how much sugar you can produce, essentially. And now I'm going to show you what happens if we allow sugar production everywhere in every internode. Just to, I mean, that's pretty much all there is, but it illustrates so much you can change the end pattern shape. It takes a little bit to run, but as I said, you keep adding parameters because you can. The end shape, it turned out, depends a lot on the growth function, and this is something you probably others have observed as well. And if you want this growth function to depend on both auxin and sugar as a metabolite, pseudo metabolite, then you have lots of possibilities to define it. So this is what happens if I allow sugar to be produced everywhere, and you have a lot more branching and growth because growth depends on, so is local, and it depends on the availability of sugar at any moment. So whether you grow or not, and then how much you grow will depend both on sugar, how much you have to consume, and also on the auxin level that you sense. And so you have really a model that is guided by both parameters. I haven't really had the chance to look at to explore the parameter space to see how much, how different the shapes can be, because of course you could change like the cost of growing. Here you have the diameter of a section of the branches which decreases, and you decided to have a production, sugar production, which would depend on the actual volume of your internode, just to see what it would give. So of course, if you have if you change this law of a decreasing section, then you will decrease the local production. So it's a very big parameter space. And actually what I would like to do is take advantage of the work done by Jeanne to run batch simulations, but instead of getting back the L string, just extract statistics, like a descriptive statistics, maybe the total length, number of branches, and one thing that Jeanne suggested we do also as a transition, to add a transition to flower state, which then for production of auxin, you have the buds, which are dormant and not producing, the active apices, which produce auxin, and then the flowers, which stop producing auxin, and also stop producing sugar, I think. And so, but then again, the rules can combine in many ways, and I think we would need a proper biological red line to follow to, but just to have the relevant configurations.
Very, very interesting. Well, for the sugar, the flowers are not well. Presumably, the flowers are not mainly producing sugar. They are most consumers of sugar. The sugar is being produced in the leaves and in the green part of the plant. So maybe according to this, maybe you should revisit a bit your different hypotheses, and but it doesn't change the overall study that you've made. But maybe if you want to go in terms of realistic plant development, then you need to take this into account more thoroughly.
Yeah.
But this is already quite interesting. People start nowadays to try to account for the combined effect of sugar and auxin. So what you have made is a sort of it's really at the frontier of what is known today about growth development. So it's very interesting. Okay, any other questions? So in the end, did you manage to recapitulate a bit the flower development, or what's your conclusion about this?
Well, for the moment, the conclusion is that I have to find the sweet spots in the parameter space to have really something relevant. So the moment you add this extra dimension, you have so many interactions and possibilities of interactions. That's why I want to go through the kind of a more systematic exploration.
Yeah,
And
yeah.
then hopefully you can get then areas that are relevant for different patterns.
Okay.
I have a question or a suggestion. I don't know. It's a bit related to Christophe's remark. So for biologists, from a naive point of view, I would say that indeed, like the sugar factories are leaves. So could you kind of compute, because you produce leaf in your model, so at least Jean showed. So if you make a basic assumption that the leaf area, for example, is a proxy for sugar production, and so at every node, you could say that the sugar concentration is proportional to the local leaf area to which this portion is connected. And then you would base local sugar concentration on this functional photosynthetic capacity. What's your...
Sure. I mean, from what we have here, what is missing is a distinct leaf module, so to make things clear. And then we can move the sugar production from the apices, where it could be, or everywhere, to only the leaves, and then let everything stay the same. Yeah, sure.
And just little remark, since we are talking about mosses, there is no flowers. Since just nomenclature and not really...
That's right. So it's a bit of the hybrid thing, as I took, we took Jean's model from mosses and then tried to pull it towards the flowers model, yeah.
Okay. Any other question to André-Claude? No, thank you very much, André-Claude. Sure. This was nice to introduce the sugar into the branching systems. And now we get to the last presentation. I think it's from Mona.
Yes. Can you hear me?
Yep.
Okay. So, okay, you can see. So this was the bell report that I was working on. So since the workshop in Lyon, I tried to work on more trying to randomize it and to see how can I make it more realistic, which it has more room for improvement. But I tried to work on the tropism for the different lens, and now I would like to give it the aspect of time. So this is defined with states and everything. So I would like to try to model it as the Arabidopsis model that we saw together in the class. But what we've been working on mostly for the project here was that we decided to work on more simplified version of the data. So using the things that we saw in the class, for example, by using external variables and also from the sampling code of Ayan that we studied together here, the sampling method of Ayan that he implemented, we try to only produce stemming only one stem, which is going to have a different kind of tropisms. And then by using the available codes, we try to do sampling in different derivation lengths. And the key is that as the stem is growing and is becoming bigger and towards larger derivation lengths, we're going to sample more point clouds. And then using these data, which is currently being generated to be able to have something around like 1,000 different plants, we're trying to use it in the context of doing point cloud compression. For example, trying to go from one time step to another. Here we can see an example of a sample point cloud after like regenerating it and visualizing it to see like it somehow gives us the same quality of like visually we can see the same quality of it. And yeah, so we're hoping that we're going to try out some very basic models with simplified versions of data and these new somehow plant data that we're trying to gather.
Sorry, Mona, I didn't get exactly what are the lines that you are showing.
So this is just a very simple stem, which is growing and is going to have random tropism at different derivation lengths. And this was like a simplified version of data that David defined. Like he came up with this idea of just trying to, for now, just try to model the growth of this stem, like without any branching, without any flowering, any more complicated things that we might have.
Okay, and the object. What is the purpose of doing this?
So the purpose is that, as we talked before, so we're trying to do the prediction of growth in time. And the thing is that we had this idea of maybe if we are able to do this for a simpler element, we can maybe extend it to more complicated elements. So the most basic element maybe in the plant could be the stem. So not taking into account any appearing of new elements such as like a branch or a flower or a fruit, but just the elongation of the stem. So this is the purpose of only like taking into account the elongation. Maybe this way the model is going to somehow be subjected to a more simpler task this way, and to see how the model is going to perform on very simple plant data, because the models that we are currently studying are more adapted to, for example, real very like big objects like cars and airplanes and these kind of stuff. So we want to see like how it does on very simple plant data.
I see. I see the overall idea, and I was wondering because maybe you don't have enough correlation in your data. I mean, to be really informative for the predictive model.
Mm-hmm.
So what I would do is, I think the idea to go to as simple a model as possible is really a good idea. But maybe I would, for instance, because in the prediction, the idea would be how is the system able to predict early, using early traits of, let's say, for instance, a drought, for instance, or something like this. Is it possible for the system to detect it in a very early phase, and then to predict, for instance, that the pace or the rhythm of the production of the different organs will be affected or decreased or something like this? And so for this, I would keep your stem, but I would add lateral elements that could be stem as well, very short or leaves, or whatever simple stuff. And then I would control the size of these lateral elements that would be affected by some external factor, and I will control the reason or the elongation of the internodes, let's say, between this. So I would introduce a sort of correlation between the growth and elongation on the main stem and the elongation of the laterals, and then see whether the system is able to detect this correlation and then to use it to predict growth.
Mm-hmm.
Because this would be a very simple plant system in a way.
Mm-hmm.
Was it clear? Or?
Yes. So you mean to say like only taking into account elongation won't help in solving the main correlation that we're trying to study and to be able to predict. So we have to add like something, a lateral element also to okay, yes.
But we can discuss this further with David, I think. But I think the overall idea to reduce the system, put a bit of randomness, and see whether the machine learning system will be able to track the overall stuff is very nice.
Thank you.
Okay. Were you finished, or did you had something other things to present?
No, I mainly wanted to show you the data because I think it's very important to like have your opinion on is this somehow like qualified as a very basic plant data or not, which I think you think is not, because we have to have like also like lifestyle elements to add to.
Yeah.
Thank you.
Okay. Any remark or question? Nothing? Okay, so it seems that we are done. Did I forget anybody? No, I think it's okay. So well, was a good session. It was very nice. Would you like to share your current models so that other people can see? I think this might be what can I do? Well, let's say if you want to share, you're welcome. I will put them on our training website, and then other people could access. If this is difficult, or let's say in the context of a publication that you want to make in the next days or weeks or months or years, then for the moment don't share it, and then it's not a problem. Okay, so those who want to share what they've done, please send your file to me, and I will make them available on the training site. Okay, and this will in any case will be kept between each other, between the group. It doesn't go outside. Okay, so any last comment or question, and before we end the session?
I mean, it could be an idea as well to give the codes for the courses online, right?
To give the code that we use during the session.
I mean, yeah, because on the online course we're gonna share our presentation of our projects, but if it's a minor project for us, like you say, it's not something we are willing to publish, it could be very interesting for the people learning to see the codes of the projects.
Okay, yeah. So yeah, so we can discuss this. And see. I will, in any case, I will make sure that everybody agrees if we publish something on the web. We need to have the approval of everybody. André, Claude, we are about to finish, and there was a general question whether there are any question, any comments before we end up this session.
No, it's good for me. I will try and find the time to make the change suggested, to make it a bit more biological. Okay. For this one model, and then I'd be happy to have the code being shared if that's useful. Yeah, sure.
Okay. Okay, so have a good end of the day, everybody. Thank you very much. This was very nice achievements. Actually, they are not all finished. I will be available if you want that I help to finish your stuff, or to finish, or I mean to progress, or to make advances in your project. So don't hesitate to send me email or to contact me. And have a good day. And Fabrice, you want?
Yeah, maybe just one remark. So this, so in a way, we made this course, the LP course, in the frame of the ROMI project, which is ending very soon. And so, since it was a European project funded by the European Commission, so we've got to produce a review, by the end of June. And so we were committed to give out some deliverables at the end for each work packages, and this like the production of let's say models was plant models was one of the deliverables, and so we decided in the end to include also the LP course into the production of the Roaming project. And so the idea is that so we discussed a bit with Christophe that we want to structure one deliverable of the Roaming project around these virtual models that are we design a way to model plans, we give out courses or lessons, and then if we just in the final document that we provide to the European Commission, we have like some even it can be even like snapshots of the models, but to say that we gave a course in the end, like so we have some people who participated to the course that were able to produce a model, and even if the model is not detailed and etc., it's just like a screenshot capture of your model, but to say that you were able to produce something in just a few sentences to say, I was trying to model the mechanics, I was trying to model sugars, I was trying to, that could be very interesting. So we will be trying to write down those reports right now. And I might contact you if we need some material to illustrate this project. And so anyway, I won't ask you a lot of work for this report. And as I told you, it might be only a few sentences or snapshots of your model just for an illustration purpose.
Yeah. Thank you for saying this, Fabrice, because I think this would be important that we can gather all this, not all, but some elements for the deliverables. Okay, so if everybody is done, then you can go and eat maybe in a couple of minutes. Have a good appétit. À bientôt. See you for the people in the group next week, and for Sony people probably next month, actually.
Thank you, Christophe.
Bye bye.
Bye bye. Thank you very much.
Thank you. Bye bye.